Movement, forces, moments and electricity. Exam, autumn term 2022. Here we go. Okay, question. Figure 8 shows a force of 70 Newton turning a lever about a point P. Okay, there's P, there's a line, this is a lever, this is the pivot or the fulcrum, and we're pushing here 70 newtons. Oh, this is a door. So this is the same as what you have with a door. You're pushing the door and there's the hinge of the door. Okay, so you're pushing a door open and the door is 40 centimetres from there to there. It's a little bit of a small, thin door, but it's a door, it's a door. Okay, here we go. And it says what to do. Calculate the moment of 70 newtons force about point P. When moments is force times distance. There we go. And state the unit. Well, force times distance. Force is in newtons times the distance, which is 0.4 meters. Force is 70 newtons. So state the units. It's going to be Newton meters. Here we go. Use the equation. Oh, they've given us the equation. Here we go. Moment equals force times distance. Oh, I've done that already. Normal to the direction of the force. Absolutely. So it has to be at the force that's at 90 degrees. If the force is over here, then you have to take components and find out how much force is at 90 degrees. That's what it means by normal. Normal means the force at 90 degrees, not the force heading in this direction or over here. So you'd break up this force into the normal force and this force that's useless for the moment. It's this, normal, 90 degrees to the door. Okay, the moment is 70 times 0.4, which is 28. And the units. The units is newtons times meters. Newtons, meters. Now, one of my students did say newtons and meters. Hold on, have I got him here? Oh, yes. Oh, it's newtons times meters. And newtons and is the same as plus. No, lost a mark there. Okay, here we go. Next one. Figure 9 shows a worker using a wheelbarrow to move some sand. Going back to my original one, there we are. To move some sand. The load is equal to the total weight of the sand and the wheelbarrow. Yes, all of the wheelbarrow added to the sand. This is the centre of mass. It's the centre of where all the sand and the wheelbarrow, so that's the load pulled down to the gravity. Cool. The centre of mass of the human will be about there where his stomach is. That's his balance point. That's the balance point of the wheelbarrow and the sand. If you were going to balance it on your finger, you'd have to have a very big finger. The load is equal to the total weight of the sand and the wheelbarrow. Yes. The effort is the force. Yeah, effort is how much how much effort you have to put in. The effort is the force that the worker applies to the wheelbarrow handles. Yes, how much effort does he have to do to lift this thing? The worker applies just enough effort to lift the load. Yes, because if he had twice as much effort to lift the load, he would flip this whole thing over. That's no good. If he put in less effort than to lift the load, it would still be on the ground and you wouldn't be able to wheel it along. So just enough to hold it there without pushing it over, without letting it go back down. It equals his moment effort, which is force times distance, equals the force times distance of the load. His moment equals the moment of the sand and wheelbarrow. Okay. The worker, just enough to lift the load here. Explain why the effort is smaller than the load. There we go. And to the mark scheme, the effort is smaller than the load. The effort is at a bigger distance. Yes. Because it's at a bigger distance, it doesn't have to be as big. The distance matters when you come to turning forces moment. From the fulcrum is where the axle is. It's the centre of the wheel. It's the piece of metal that goes through the middle of the wheel, also called the pivot. The effort is at a bigger distance from the fulcrum than the load. Yes. Also, the reverse argument is true. The load is at a smaller distance from the fulcrum than the effort. Right, that's the opposite way around of explaining it. Magnitudes of moments are the same. Yes! Force times distance equals force times distance. Allow wheel, axle, pivot for the fulcrum. Yes, of course. There we go. And next question, it says... some sand falls down and sticks between the wheel and the axle. Yes, you're bound to get sand all over. Between the wheel and the axle? Oh, you don't want that to happen. That's going to be grindy. That's all the ball bearings going to have trouble with, all the sand in between, in the middle of the wheel. State why it might be harder to push the wheelbarrow along when there is some sand between the wheel and the axle. Friction. There will be more friction between the axle and the wheel inside the bearing. The bearings are all the little balls inside between the axle and the wheel that help it go round easy. Cool. Question 2. A ball has a mass of 0.046 kilograms. So 1, 2, 3, 46 grams. Okay, it's quite a light ball. Maybe a super ball, big bouncy ones, plastic things. Calculate the change in gravitational potential energy when the ball is lifted through a vertical height of 2.05 meters. So, ball on the floor, we're going to lift it up a distance of 2.05 meters, which is about as high as I can reach when I'm on my tiptoes. Okay, so the change in gravitational potential. Oh, what's the formula? Well, luckily, they've given it to us. Change, that triangle means change. It's called delta, it's a Greek letter, you don't need to know that, it just means the change. The change in gravitational potential energy equals M. Oh, what could M be? Mass. M is the mass, so we need the mass times by G. Now the G for gravity. On Earth, 9.8. You can also, for most questions, just simplify it and put it as 10. In the mark scheme, you're allowed 10, 9.8, or if you're in England, 9.81 meters per second squared. Yes, it's less when you're in the equator. In Portugal, it's more like just 9.80. But 9.81, 9.8 and 10, they are all in the mark scheme. You're allowed to use any of those, but you have to use one. Don't use 1.6 meters per second squared. That means you're on the moon. Definitely don't use it. Okay, so delta H. Oh, what could H be? Oh, H is the height. And it's delta, it's the change in the height. The height has gone from 0 to 2.05 meters. Right, okay, and then we've got to times these all together. So, mass times G times the height. And yes, they don't give you G, you have to remember it. And so let's see what this student has done. He's done the mass in kilograms. Yes, that's fantastic. And he's done times by G. Oh, no, he hasn't. And he's done times by delta H. And so he's not got the right answer. Oh no, look, there's a G here. It's gravity because, oh, well. Okay, the ball is released. Calculate the kinetic energy of the ball when the speed of the ball is 3.5 meters per second. Oh, okay. So this one, very unfair, because I just grabbed all the questions that were about forces and motion and electricity for this autumn exam, and I didn't look through the questions because that would change how I did my revision classes. I'd feel a bit weird if I was revising something I knew was in the exam. Anyway, so I know some people do. They only revise the things that they've put in the exam, but in a GCSE it's going to be random questions. You don't know what's going to turn up, you just take what happens, and sometimes it's going to be stuff you don't know. Anyway, so in this case, my students couldn't get these 3 marks. Oh dear, but have a look. They did good. Anyway, kinetic energy, KE, equals a half times m times v squared. There was no way my students were going to guess that. I have told people, if there's 2 numbers, times them together. And some of them did that, and it's just not going to work in this case. It's advice that works for some questions about a quarter of the time. Just times the two numbers together. Anyway, half times m times v squared. So we need to put into a calculator half times, what was the mass of it? 0.046 kilograms times the velocity squared, 3.5 meters per second squared. So 0.5 times by 0.046 times by 3.5 times 3.5. Go! Okay, here we go. Calculator. Time. 0.5 times 0.046 times 3.5 times 3.5 equals 0.28. 0.28. 0.28. What's the units going to be? Energy. Joules. Capital J, after the French gentleman, Mr. Joule. The ball bounces several times. Okay, what happens if the ball bounces? Figure 15, over the page, shows how the height of the ball above the floor changes with time. Here we go. Okay, and bouncing ball time. There we go. So this is the height in meters. Always have a look at the axes before you carry on reading. Height of the ball, yes. So you drop the ball goes down. Of course it does. And then it bounces up, and then it goes down, and then it bounces up, and then it goes down, and then it bounces up, and then it just stops. Cool. But we've done this as like a video, so we could see moving the time axis along. So rather than just a line going, hold on, here we go. Bouncy, 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 bouncy. And then you can't see anything. You can't do any maths with this bouncy, 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 bouncy. This is no good. So they've stretched it out with the time axis along here. So we can actually see the first bounce. And it goes up again. Does it go all the way to the top again? No, because when it hits the ground, energy is lost. The sound of boing as it hits the ground. And also, the ball heats up as it hits the ground. That's why in squash, when you're playing squash, the ball gets quite hot after a few games of playing squash and other things. But squash, you can really feel it even with your skin. There's go bouncy, bouncy, bouncy. So it doesn't even bounce up 50%. Maybe this is a tennis ball now. Okay, here we go. Use figure 15 to estimate the maximum height that the ball reaches after the first bounce. Okay, well, it starts from here, goes down, bounces up to there. So this is just a little bit smaller than 1 meter. A little bit smaller than 1 meter, 0.8. Well, that's a little on the small side, 0.8. But it does say in the exam, very lucky that student, it does say any value between 0.8 meters and 0.95 meters. There was one student who put 0.99 and didn't get that mark. Oh well, if it was 0.99, it would definitely be up. It's the middle of the ball you're doing the distance with, because notice here, it's the middle of the ball. Cool. Because the gravitational potential... Hold on, what a question. Explain why the ball does not bounce back to its starting height of 2.05 meters. 2 meters and 5 centimeters. Why does it not? Because it loses energy. Oh, we've said the word energy. Do we get a mark just for saying the word energy? There we go. And the mark scheme's in. Okay, answer. Explanation linking the ball has lost energy. We can't say the ball's lost energy. Identification of what has happened to the energy. Oh, well, what's the energy turned into? The energy is transferred to the surroundings of the ground. It's heated up the air, heated up the ground. The air? Well, a tiny amount. Thermal energy, that's heat energy. The ball heats up, just like saying squash balls, they get hotter. Heat and sound, yes. Yeah, well, thermal energy, heat energy, same. The system is not 100% efficient. No, if it was, then it would bounce up to the same height that it started from. Balls aren't that good. Bounces is not 100% elastic. No. If it was 100% elastic, it would bounce back up to where it started again. Balls don't do that. Not when you just drop them out of your hand. You have to throw them downwards if you want them to come up to where they started again. Squashing the ball... Squashing. Yeah, squashing happens. The ball changes shape when it hits the ground. That's why it loses energy. The ball or the ground. Excellent. Okay, and so what did the student say? Here we go. Because the gravitational potential energy... Okay, it's got the word energy and acceleration aren't high enough to give the ball the energy it needs to get back to the... Oh. So that one didn't work. Next. Question 3. Complete the following statements using words from the box below. Electrostatic. So that's electricity. It's not moving. Static electricity. This is an experiment where you rub a ruler in your hair and a tiny little piece of paper on the table dance up and down to your ruler. If you've rubbed it enough on your hair and it's a dry enough day, you don't want a humid day, it's a dry enough day because humidity allows electricity, static electricity to move through the air. And if you put it just a few millimeters above smallest pieces of paper you could make, and it dances backwards and forwards. Electrostatic attraction, that's what we use to paint cars with, if it's on robots and a mass production thing. Friction, the force that stops things moving. Gravitational force is the force that pulls things towards the centre of the earth. Magnetic forces, that's for the magnet that holds your fridge magnet to your fridge. Here we go. Let's have a look, see what my students said. And there we go. Okay, so my students said the force that keeps the Earth in orbit around the Sun is gravitational attraction. Absolutely. The Sun is thousands of times bigger than the Earth, and it pulls using its mass. Mass is bigger they are, the more gravity they got. The force that opposes motion between two surfaces, stopping things moving, it's friction. Excellent, good mark. The force that can move small pieces of paper towards a plastic comb, or I prefer, magnetic forces. Oh, static electricity. That one didn't work. Question 3. Next, question 4. Question 4. Now, this one scared me when I saw this one happening in the exam, and I thought, oh no, they've done springs being squashed. Whereas what I taught was springs having weights made longer, extending. And I thought, oh no, this one's going to cause trouble. Anyway, we have to see how my students got on, because, you're going to get questions on stuff you've never done before. Wheelbarrows. My students don't even know what a wheelbarrow looks like. They've never seen one in their life, but they did okay on the question. Well done, guys. Figure 14 shows a spring standing on a table. Spring, table. This is actually quite a good idea, because this is quite simple setup to do. But less usual. Usually you make the spring go longer. Extension. On a table. Okay, there's the spring. There's the spring. There's the ruler. Hold on a minute. Somebody's using a really rubbish ruler that's only got in centimetres. That's weird. Okay, it says millimetres. Oh, okay, here we go. Oh yes, because 10, 20, 30, 10 millimetres, 20 millimetres, 30 millimetres. Why is it not in individual millimetres? I looked at this and I thought, well, that's just, someone's chosen a primary school ruler. Bad idea, bad person. And why is it so far away from the spring? We shall find out in a minute when it asks us how to improve the experiment. Weights are added to the spring as shown. Okay, in figures 14b. Yeah, I've still got to get that apparatus. It's not come through the post yet. Don't know if I'm going to get it before Christmas. Let's check 14b and 14c. A, B, C. Yeah, putting weights on it. More weights. No weights at all. Okay, estimate the original length of the spring as shown in figure 14a. Okay, it's about 50, isn't it? About 50? Okay, and the mark scheme says you get the mark if you say anywhere between 50.0, you don't need the 0.0, 50 to 55. Anywhere between 50 and 55 millimetres, inclusive. And this student here, it says 51! Yay! So that's good. Okay. Yeah, just maybe just a little bit more than 50. Okay, anyway, it's up to 55. 55. Anyway, up to 55. Next says, describe how the reduction in the length of the spring when the weights are added can be determined. Okay, how are you going to determine how much it's gone down by the reduction in length? Okay, so the answer machine says, okay, here we go. A description including note the original length, note the final length, and subtract. So how big it is to start with, subtract how big it is now. Cool, nice and simple. Yeah, absolutely. So it's this, take away this, gives you how much it has reduced by. Yeah, nice and easy, nice and simple, nice handwriting. Oh my gosh, what's this? Okay, add a light pointer to the top of the spring. Now this is a good idea when you're improving the experiment. This is a great thing for improving the experiment. You don't get any marks for that at the moment. Okay, all right. Point horizontally to the ruler. Yes, this is how you improve the experiment. This is not what it's asking. It's asking how to you get the reduction, how to get the reduction in length, how to get the answer, the number. Right, the weights are added to, okay, right, to take, to fake, I'm not sure. Okay. No, I couldn't read that bit. Look at the measurements that the pointer is pointing at. Right, okay. Where is it pointing at? And subtract the measurements from the original. Excellent. He's got two. Absolutely. Get the original, subtract where it went to. Wow, that was difficult to decipher. And then he put some more up here. Measurements from the original, measurement of the spring. He definitely got both marks using the most amount of writing that anyone could possibly use. But anyway, good. He got the marks. Next part. Oh. Next part. Oh, it's a rocket. Hold on, that goes to the rocket. No, it doesn't go to the rocket. No, there it goes, next part. State 2 ways the experiment procedure could be improved. Oh, now we need to improve it. Now we need to talk about pointers and using a different ruler. And there are many ways of getting the right answer. Any two from. Use a ruler with a smaller millimeter divisions. Yeah, a normal ruler that's got millimeters in it, really. Okay, use interim values of weights. So rather than chucking on these heavy weights, use much smaller weights to go about it. So the question had you putting on, okay, some weights, and then some more weights, some heavy weights, and then some more heavy weights. Use some lighter weights in between. You can get a graph and stuff. Add more weights to increase the range. Yeah, get more results. Move the ruler closer to the spring. Yes. Use a pointer. Yes. Repeat and average. Oh. Lots of my students said repeat. They didn't say what you do with those repeated. So you do it every experiment at least 3 times, and then you add them up and divide by 3. You average the results, and yes, none of my, it was, they all said repeat, and none said average the answer. Okay. Ignore if someone says do it more accurately. Well, because you have to explain how you're going to do it more accurately. Yeah. Anyway, here we go. Add fixed values of weights. Eye level, no parallax. Yes, put your eye down level with the ruler to get a good level with the ruler so you can get the measurement right. Especially if you're using millimeters on a ruler. Okay, here we go. And what did my students say? They said... Okay, here we go. And they said, use a pointer such as a toothpick to help give a more accurate result. Nice, good mark. They also said plot a graph and repeat experiment. Repeat the experiments, then average those 3 or 4. Oh, they didn't say that. To find the anomalies. Yes, if there's any anomalies, you cut them out and you don't use them. Using a graph, good. Now more precise. Oh. Okay. Give one reason why the reduction in length eventually reaches a limit at the more lengths are added. And the answers say the coils are pushed together and they're touching. Yeah, once they're touching, the spring won't go down anymore. The spring is fully compressed, cannot be made any shorter. Yes. When you're pulling it, it reaches its elastic limit. When you're squashing it down, the spring coils are just touching and they won't go down anymore after they're touching. And the student said the spring would break. It's going to break when you squash and not be able to go back to its original shape. This is true if you're making the spring longer. If in extension, in compression, no, the coils just touch. Next, question 5. Question 5. A firework rocket contains a solid fuel, it can be liquid fuel, inside a cardboard tube. Yeah, why are we not doing this one at school? Explosions, burning, bits of spark. Definitely not doing this at school. The burning of the fuel creates a thrust to propel the rocket upwards. I like it when it talks about rockets because my students are interested in rockets, space rockets, going to Mars and all that stuff. Science fiction, here we go, rocket. Burning fuel, burny. Solid fuel, yes, so it's there and it burns away and the solid becomes gas and comes out the back and this looks like a firework. Okay, here we go. A firework is kind of rocket. You can buy rocket fireworks. Rockets are like fireworks. Yes, one of the space shuttles blew up, didn't it? Scientists, and they stopped making them anymore because they realised they were dangerous and they should have talked to an engineer. I've got a whole YouTube video on that. Scientists can refer to several different quantities when describing the motion of the rocket. The mass of the rocket, the energy of the rocket, the speed of the rocket, the force of the rocket. Which one of these quantities is a vector? So, which one can you say it's got positive direction or negative direction? Well, mass, you can't have negative mass. Energy, you can't have negative energy either. You can't have energy going north. And you can't have mass going north. Weight goes down, but not mass. Mass is just how many atoms you've got. Speed, oh no, it's velocity is the vector. And you can tell that it's a velocity is the vector because the V makes an arrow. Velocity is the vector, speed is the scalar. We want a vector, so it's not the mass, it's not the energy, it's not the speed. Oh, it's going to be the force, because you can have force pushing you north, or force pushing you to the left, or force pushing you to the right. Force is definitely a vector. Okay, only one of these is a vector. Complete the sentence using one of the words from the box. The vector way. The vector quantity is force, ticky. Before the fuse is lit, the total weight of the rocket, including the fuel, is 0.7 newtons. N for newtons, named after the guy that did all of the physics for force, Mr. Newton. The gravitational field strength is 10 newtons per kilogram. Yes, on Earth, well, 9.81 if you're in England, but it kind of rounds to 10. I don't like the rounding stuff. Anyway, 9.8 is what I teach my students. It's true of all planets, all people on the Earth planet. Go to the moon, 1.6. Go to other planets, different numbers. Complete the sentence by putting a cross in the box next to your answer. The total mass of the rocket, including the fuel, is at. So they do this so they can get computers to mark the exams. More and more, it's going to be less humans marking it. It's going to be a computer marking it, because computers are going to do faster and cheaper than employing a human, and more efficiently, so long as people put the right kind of cross in. The total mass of the rocket, including fuel, is... Okay, F equals ma, yes. F equals ma. The force or mg. Force 0.7 newtons equals 10 newtons per kilogram times by, because that's the G, the mass. Hold on, I should put the M in there. M times 10. So a number times by 10 equals, right, okay, so I'm going to divide 10 both sides. Okay, and I get 0.07 newtons. Oh, no, we'll do it again. Okay, here we go, do it again. 0.7 newtons divided by 10 newtons per kilogram equals M. Newtons divided by newtons. The kilogram is divided by twice, which is why it ends up in the top. 0.07 kilograms equals the mass per chain. And this student absolutely did it right. He, first of all, thought it was a 7 kilogram rocket. 7 kilograms? So it's as heavy as a full rucksack? No. Yeah, we're much lighter than that. It's 70 grams. That's about a firework. Yes! There we go. There is a resultant force on the rocket of 0.5 newtons upwards. The result. So therefore there's a force downwards, gravity, and then there's the thrust force upwards, and the result is 0.7 upwards when it takes off. Okay. The arrow on the diagram shows the size and direction of the force of gravity acting on the rocket when it takes off. So we've got a force downwards. Here we go. We have got a force downwards of 0.7 newtons, that's due to gravity, and we've got a force upwards that gives us the resultant force of 0.7. So we've only got one mark here because it's the resultant force we need. So there should be an arrow pointing upwards. Yes, arrow pointing upwards. And it should be 1.2 newtons is the force, giving us a resultant. 1.2, take away 0.7, there's the 0.5 as the result. Here we go. Add another arrow to the diagram to show the thrust. Now see, if my student was correct, if there's 0.2 up and 0.7 down, then the down is winning. The rocket would not go up. But with my rocket, it's got 1.2 newtons up, beating the 0.7 newtons down. The gravity is beaten by the thrust. How much is it beaten by? That's where the 0.5 comes in. He's only got one mark out of the possible two. You should label the arrow with the size of the thrust. There we go. And the mark scheme says, force 0.07 kilograms. We've done those guys already. Arrow pointing vertically upwards. Value 1.2 newtons. Written near the arrow. Marks are independent of each other. So long as there's an arrow pointing upwards, you get one mark. And here we go. Question 6. Answer the questions with a cross in the box you think is correct. If you change your mind about the answer, put a line through the box, and then mark your new answer with a cross. Yeah, this is so you can do it in pen, because pencil. Some exams use pencils, some exams use pen, and some exams use, anyway, this system. Okay, the magnitude and direction of a force can be represented by a vector, which is a line with an arrow. There's another one, in a different direction. Same magnitude, different direction. Larger magnitude, same direction vectors. They're arrowy, pointy things. Forces and velocities, stuff like that. the magnitude and direction of a force can be represented by a vector. Figure 22, there it goes. Figure 22 shows the forces acting on 4 identical trolleys. Yeah, a little wheelie thing, like a shopping trolley, but in miniature for physics experiments. Trolleys. The arrows show the magnitude and direction of the forces. Which diagram shows a pair of forces that will produce zero acceleration? Okay, so this one's being pushed a little bit in the right direction and pulled lots in the right direction. This one's definitely going to accelerate right. This one's pulled a little bit to the left and pushed a little bit to the left. It's definitely accelerating to the left. This one is pulled a little bit to the left and a lot to the right. This one's going to lose, so this one's going to win. It's going to be accelerating in this direction. Hold on. Oh, this one is pushed to the left and pushed to the right. It's just going to get squashed. This is the one that does not change. And, oh, well done, my students, that got that one right. Question 7. There we go. Answer the questions with a cross. Oh, yeah, same. Okay, this is a student doing an experiment. A student determines the density of a liquid. The student puts an empty measuring cylinder on a balance. Figure 10.A. Okay. It should really be called a weight balance. Anyway, the student then adds liquid to the measuring cylinder, 10.10B. 10B. Okay. So he's got the cylinder on there, finds out how many grams just the cylinder is, and then he puts some liquid in there. Oh no, look, this cylinder hasn't got all the little measurements in it, just like the one we had previously. I think that's going to be needed. Okay. Calculate the mass of the liquid added and the volume of liquid added. Well, the mass added is this one, take away this one. So that's 230, take away 201. And what do we get? Oh, 29. Yes, absolutely. Well done. And the volume, well, about halfway between 20 and 30, so about 25. Yeah, grabs the answer things. 25. Oh. Okay. And there we go. Nicely done. 29, 25, yes. Which equation should the student use to calculate the density of the liquid? Density equals mass divided by volume. Yes. Hold on a second. Did the student get it right? Okay. Density equals mass divided by volume. Yes. That's the right one. Tick. State 2 improvements that the student could make to this investigation. Use measuring cylinder with smaller units. Yes. Yes. Smaller measurements on your but better measuring cylinder. Express mass of measuring cylinder as 0. Okay, yes, tearing it using the 0. Yes. Good mark. Well done. Next question. Question 8. A student is investigating a filament lamp. That's the light bulbs that's got very thin wire in it. It's called thin wire. It's called filament. Complete the sentence by putting a cross in the box next to your answer. The current in the filament lamp is the flow of. So what's moving through the metal wires in circuits in the walls, in the wires that you plug into your phone to recharge your phone? Is it protons? No, the protons are the big things in the middle of the atoms, little p. The protons and neutrons are in the centre of the atoms. What's the name of those ones going whizzing round? The protons and neutrons are in the middle. They can't move. They're too big. They're 2,000 times heavier than this thing going around. Oh, it should be drawn much, much smaller, but, hey, I can just small it. So the whole atoms are moving? No, it's the electrons. Yes, electrons. Electrons making electricity when they move from one place to another. Cool. The electrons are free to move when it's a metal. One proton, one neutron, one electron. This is an isotope of hydrogen. This would not conduct electricity, but the electron can move for chemistry. That's chemistry. You need metals, copper metals, to do the wires inside things, or inside the filament lamp, the metal that can take the heat of it getting so hot it's white hot and yet not melting. That's tungsten. It's a tungsten filament lamp. It's the only metal that's really good at being thin and very, very hot. Nowadays we use light emitting diodes, LEDs. The students, or of course there is also the strip lights called fluorescent lights. That's the long tubey ones that you get in hospitals and in shops. The student uses this and also kitchens. This circuit in his investigation. Here we go, in the investigation. Okay, what have we got? So we've got several cells. That's one cell. That's two cells. That's lots of cells, making a battery of cells. Excellent. We've got a resistor, and it's got an arrow through it, so that's a variable resistor. That's a dimmer switch. Louder, not so loud. Brighter, not so bright. Turny circle to make it more or less. Cool. There's my light bulb, my filament light bulb. It's got an X to show it's an indicator light bulb. There's this meter that counts all of the electrons. It's the ammeter, counting the amps. Nicely done. And the voltmeter is always in parallel with the thing that it's finding out how much push, how much volts they've got. Ammeter can be there, or you could have drawn it there, or you could have drawn it there, or you could have drawn it there. Anywhere where all of the electrons have to go through it. The voltmeter has to do this in parallel to find out the volts of that particular lamp. Well done, that student. Quite a lot of my students got them the other way around. Okay, more work necessary. Here we go. The normal operating potential difference. Potential difference means the same as voltage for GCSE. When you do A-levels, there's some differences. And the current of the filament lamp is 6 volts. The potential difference is 6 volts. Okay. And the current is 0.4 amps. Okay. Calculate the energy supplied to the lamp under these conditions. Energy equals, times them all together. Energy equals ITV. E equals ITV. Current times time times voltage. Do apologise to my students at that point. I don't think I've said them that equation. But this student, he just timed them all together and got it right. Paching. Well done. Here we go, next one. Okay, current and voltage, they're changing. Where it's a straight line, that's ohmic law. That over this part is where V equals IR. And obviously, because it's heating up, it doesn't say ohmic for very long. But we use V equals IR anyway, because it makes the maths easy. Here we go. Calculate the resistance of the lamp when the current in the lamp is 0.3 amps. 0.3 amps is down here. 3.234. 0, 1, 2, 3, 4. Excellent. So that's 3. Okay. When it's 0.3 amps, the voltage is 3. The resistance equals potential difference divided by current. Resistance equals V divided by I. Some of my students didn't use that equation, they gave it there. Resistance equals voltage divided by current. Hold on. Wrong way round. I've gone back to the wrong question. That one's done. There it is. resistance, voltage divided by current equals resistance. It's the voltage divided by the current. It says in the equation. Oh no. So anyway, didn't get that one. Okay, keeps going. Question 9. Okay, here we go. Question 9. Some questions must be answered in cross. Put the cross in. We've done that. An electric water pump, there's a water pump somewhere, is powered by 200 volt mains supply. Yes, 210, 220, 230, 240, 250. That's the voltage for all of the world, apart from America, which is only 110 volts. That's why you can't use things from America and plug them in England or anywhere in Europe, because they go and then stop working, never work again. You need a transformer. Figure 12 shows the inside of the plug on the cable to the pump. Oh, this is very much the UK type of plug. It's got a fuse. The live wire goes to the fuse. The earth wire is yellow and green, goes to the top one, the longer pin in the 3-pin plug. So that's the live wire, which is brown, and that's the blue wire. Blue is neutral, because if you do chemistry, you know that water is neutral and water is blue in oceans, and so therefore water blue, water neutral, pH 7. There we go. Next one. One wire in the plug is the earth wire. The other two wires are the live and the neutral. Paching! Well done. Here we go. Next one. Describe the purpose of the component labelled X. Describe the purpose of it. What's the purpose of it? What's it there for? The component labelled X is the fuse. 1 mark. We use it to save, in this case, electric water pump. That's true, but it's not in the mark scheme. It's there to melt when there is too much electricity, when there is a surge of electricity, and then it melts. Okay, didn't get that. We've got to write everything you know. Question 10. Sam and Joe are on their bikes. They are on a flat, straight road. Okay, there's Joe's line and there's Sam's line. Sam's just horizontal the whole time. He's staying the same velocity the whole time. He's staying the same speed the whole time. Okay. Joe is stationary. Is Joe stationary? Oh yes, Joe's going 0 meters per second velocity. He's going 0 meters per second for nearly 5 seconds. Okay. Joe is stationary when Sam rides past at a constant velocity. Okay. At 10 meters per second. Joe waits for 4 seconds. Okay, so this must be 4 seconds he's waiting. Let's have a look. 1, 2, 3, 4. For 4 seconds. 1, 2, 3. For 4 seconds, Joe is just waiting. He's just letting Sam get ahead of him. Maybe Sam's his younger brother. Joe waits for 4 seconds and then follows Sam down the road. He's chasing after him. This is a velocity time graph of their motion. Okay, so at first, 4 seconds, Joe's just waiting as Sam is zooming along. Then Joe, after 4 seconds, says, right, I'm going to beat you now. And then he starts accelerating. He's going faster, he's going faster, he's going faster, he's going faster, he's going faster. Then he gets to his top speed, and he's now at his top speed catching up with Sam. Okay. How far did Sam travel during this 15 seconds? Well, Sam's going at steady velocity. So velocity... Oh, they've got the equation. Distance equals velocity times time. So his velocity is a steady 10 meters per second, and he goes there for 15 seconds. So it's 10 meters per second. Always put the units in times. 15 seconds, which the seconds cancel, giving you 150 meters. Yay! Well done. Next part. Here we go, over the page. Cool. It says, at which of these times is the resultant force on Joe bigger than the resultant force on Sam? Well, Sam's going steady speed, so there's a resultant force is 0 the whole time. He's going a constant steady speed. If there's a resultant force, he will accelerate or decelerate. Okay, so it's when is Sam going steady speed and yet Joe is accelerating? Hold on, I'm getting back to the graph. Oh, last page. And it's there. Okay, go to the graph. Here we go. And the graph says, okay, at this point, Joe is accelerating from 4 seconds until, what is this, 10 seconds. He's accelerating. So this is when he's got a resultant force on him. He's getting faster because of the resultant force. He's really pushing those pedals. So, is it at 3 seconds? No. 7 seconds? No. 11 seconds? No. Hold on. Yeah, it's 7. Any time between 4 and 10, he is accelerating. There's a positive force pushing him faster and faster. Oh, 15's not right. Okay. No, at 15 seconds, he's doing steady speed. And so, this is steady speed. No force, no acceleration. No resultant force and no acceleration on him. Oh dear, that didn't work. Okay. For how many seconds was Joe accelerating? For 6 seconds. Yes, between 4 and 10. That's correct. G. Calculate Joe's acceleration during this time. So acceleration is change in velocity divided by time. So change in velocity is he's gone from 0 to 15. So it's 15 divided by 6. 2.5. Yes. The diagram shows the horizontal force acting on Joe at one point while he is accelerating. Yes, the forward force is 100 newtons, and of course, due to the friction, a little bit of air friction drag, but also lots of friction at the wheel and friction inside his body there'd be friction as well, but now inside all the moving parts of the bicycle will have some friction. Okay, calculate the size of the resultant horizontal force acting on Joe. So it's this force against this force. Who's winning? Oh, 100 newtons beats 30. It beats it by 70. Gee. The total mass of Joe, his heavy bag and his bike is 55 kilograms. Calculate the total weight. Oh, gravitational field is 10 newtons per kilogram. Every kilogram gives 10 newtons. So we've got F equals ma, and for gravity it's F equals mg. Okay, so we need the force, which equals 10 newtons per kilogram. That's the G. Times the mass. What's his mass? Oh, 55. 10 times 55. 550. Absolutely. Newtons. Because that's 55 kilograms. And the kilograms cancel each other out. Kilograms divided by kilograms, they cancel each other out. And there it goes. On another day, Joe is riding the same bike on the same piece of road. This time he does not have the heavy bag on his back. Oh, so his mass is less. So when he's got less mass, F equals ma, he'll find it much easier to accelerate. He finds that it's easier to accelerate. Explain why Joe finds it easier to accelerate. In this day, Joe's mass and weight, well, it's the mass that matters because it's F equals ma. F equals ma, and so the acceleration equals force over mass. Okay, is smaller. The mass is smaller than before, so he needs less effort, less force for the same acceleration as last time. Yes, F equals ma. Force equals mass acceleration. Fantastic. Absolutely. Much better describe them in the answer sheet. Explanation linking combined mass is less. Yes, the bicycle and the guy is less than the bicycle carrying the bag. Smaller force is required for the same acceleration. Yes, because his mass is less, you need less force to accelerate the same. Or more acceleration for the same force. Yes. Ignore references to weight. No, weight is downwards. Friction? No, it's the same bicycle. No, same friction. Or backwards force. No, it's the same friction. Because it's the same bicycle. Ignore easier to accelerate as in STEM. STEM? Less force needed to accelerate. Yes. Go! Well done, guys. Great marks. I was impressed. Everyone did better than I thought. Phew. Well done.